Hi, my dear students. Today we are going to continue talking about acids and bases. And in our session today, I'm going to touch few points that are going to be used in the calculations for strong acids and weak acids, or strong base and weak base. So before we go into these calculations, some few concepts has to be clarified before that. Let's start with them one by one. The first term that I'm going to talk about today is what is called self-ionization of water. Sometimes it is called auto-ionization. It is the same, either self-ionization or auto-ionization of water. Where from this idea comes and what does it mean? First of all, we all know that the pure water is not conducting electricity, while tap water conducting electricity because of the presence of some ions in it, like chloride ions. So what is actually responsible for conducting electricity in the tap water is the ions that are added to water in order to kill bacteria and to kill other germs in it. So these ions are responsible for the conductivity of water. I'm here talking about the tap water. While if you are talking about pure water is a substance that only made up of water molecules with no other ions or with no other species in it. So since H2O molecule is a neutral molecule, so it is not supposed to conduct electricity, because as we all know, conducting electricity needs charges to be moving within the solution or the medium, wherever it is. Since water is made up of water molecules, which are neutral molecules, they don't carry charges. So we will not expect water to conduct electricity. Here I'm talking about pure water. Actually, this is not 100% correct, because it was found that in pure water, some water molecules, I'm saying some water molecules, react with each other as an acid and a base. According to what? According to the definition of Bronsted and Lowry. Bronsted and Lowry said, if you go back to the previous video, we have defined the acid as a proton donor, while the base is a proton acceptor. In this case, two water molecules, one of them, I don't care which one, will act as an acid and the other will act as a base. Suppose this one will act as an acid, so it would what? Donate H plus, so it is the acid here, to what? To the other water molecule. This will produce what? This H2O would become H, this one would become H3O positive, which is called hydronium ion. And this water molecule, after donating H plus, the remaining part of it would be what? OH negative, hydroxide ion. Hydroxide ion. If we look to the mole ratio between H3O plus and the OH minus, by the way, this one would act as a base, Bronsted-Lowry base. This is acid because it donates H plus. This is Bronsted-Lowry base because it accepts. This reversible arrows indicates that this process is a very weak one, weak process, weak reaction. All the time we have learned before, when we were talking about equilibrium, that equilibrium is taking place for what? For weak substances or weak reaction or weak process. This means all the time weak reaction. Weak reaction, so that's why we use a double arrow for it. Now, if you look at the mole ratio between H3O plus and OH that are found in water, pure water, you would find it 1 to 1. One mole here and 1 mole here, so 1 to 1. 1 to 1 means that as much concentration of H3O you would find in pure water, you would find the same amount, the same concentration for OH negative since they have the ratio of 1 to 1 between both of them. It was found that at 25 Celsius, it was found that the concentration of H3O plus in pure water equals 1 times 10 to the power minus 7 molar. And since the ratio is 1 to 1, as we said before, so what concentration I would expect for OH in pure water? It would be the same. OH negative would have a concentration again of 1 times 10 to the power minus 7. From our discussion through the equilibrium topic, we said if we want to write the equilibrium expression for this reaction, we should write K equals, I am writing the equilibrium expression, equilibrium constant expression for this reaction. We said that equilibrium constant expression all the time relates products with reactants. Here, you should put products here up over what? H2O. If you remember also well, when we were talking about equilibrium, that any liquid or solid, we will not include it in the equilibrium constant because their concentration will stay almost the same in the reaction. So we can eliminate anything, either liquid or solid. In this case, the difference here is that these two are liquid state, but this one is AQ and this one is also AQ, aqueous, which means that the equilibrium constant expression should only contain what? H3O times OH minus. And if you eliminate this, this would become what? KW. W represents what? Represents water. So what do we call this one? We call this expression as the ionization constant expression for water after we eliminate what? H2O from this side. So this would be the ionization constant. Why do we eliminate water? Because they are, as we said, liquid. And now we put W here to represent that this constant, this expression is only used for what? For water. What would be the value of Kw at 25 Celsius? Since H3O is 1 times 10 to the power minus 7, OH 1 times 10 to the power minus 7, so Kw would be 1 times 10 to the power minus 7, 1 times 10 to the power minus 7 equals 1 times 10 to the power minus 14. This is the value for Kw at 25 Celsius. We will all the time use 25 Celsius as a reference for us. Now, this value represents the Kw, which is the ionization constant value for water, which represents the product of multiplying concentration of H3O plus OH negative within pure water. This value, this is the important thing. This from here, from the point that I'm going to discuss with you now, from here, you should know that calculations starts from this point. This value all the time should be maintained, which means that in any case that H3O plus increased in water, what would you expect for the value of OH to be? What will happen to OH concentration in order for this value to remain constant as it is 1 times 10 to the power minus 14? I think if this one increased, this one should what? Decrease. And you can look at either away from another way. If OH negative increase in water, H3O would decrease. Why is that? to remain, when you multiply them, to remain, or to maintain the same value, which is 1 times 10 to the power minus 14. The question is, how could H3O plus increase in water or OH negative? Suppose that you come to water like this. Suppose that I have a cup of water, which is containing H3O plus OH negative. This is water. And suppose that you add an acid to it. An acid, any acid, is a source of which ion of these two? I think acid is a source of H3O. If you want to check that, suppose that I am dissolving HCl here. HCl, when react with water, it would produce what, according to Bronsted-Lowry? It is what? Going to give H plus here. This will donate H plus because it is an acid, according to Bronsted-Lowry definition. An acid is a proton donor. H2O would accept this, producing what? H3O plus Cl negative. So when you dissolve HCl in water, what will happen is that H3O here would increase. The value of H3O would increase. Why? Because the acid is a source of H3O plus. So on the other side, what would you expect for the value of OH? OH would what? Decrease. Why is that? For the Kw to stay constant, which is 1 times 10 to the power minus 14, any change happens to H3O, whether it is increasing or decreasing, would have an inverse effect on the OH negative. Inverse means if H3O increase, OH decrease. If H3O decreased, OH will increase. Again, to keep this value constant all the time. What happens if you add to the water? If you come to the water, the same thing, which is also containing H3O plus OH negative, and you add a base. A base like, for example, NaOH. NaOH is a source of what? NaOH, or any base, not NaOH only. NaOH is a source of OH negative because when it ionized in water, it would give OH negative. So in this case, when you add NaOH or any base, OH value would increase. So this would cause to what? To decrease in the value of H3O, again, for this value to keep constant all the time. This is what happened. This is how you can change H3O and OH within any sample of pure water. Either by adding acid, H3O would increase, causing OH to decrease in concentration, or by adding a base in which it will cause the increase of OH negative, and the other side, H3O would what? Decrease. In this case, we call this solution, any solution made up from dissolving an acid in water, it is called what? Acidic solution. So here we can describe this case here as we will have an acidic solution. So acidic solution means any solution that contains more H3O plus than OH negative. Why? On the other side, this is called what? Basic solution. Basic solution. When we get basic solution, if OH negative concentration increase compared to H3O, if it is increased and becomes more than H3O plus, so it is a basic solution. Remember that the original case is both of them are equal in pure water. If H3O increased over OH minus, so it is an acidic. If OH minus increased over H3O plus, so it is what? A basic solution. These are the two types, the main two types of solutions that we are going to talk or to make our calculations. This is the first point I want to talk about. Now, let's go to the second point, which is what? pH. pH is a measurement for acidity of a solution, or how much acidic is the solution. pH is a way to measure how much acidic is the solution. How can we calculate? Does it has a formula? Yes. pH for any solution could be given by what? Applying this formula, minus log, natural logarithm to the base 10, concentration of what? H3O plus in the solution. So only you need what? You need to know the value of H3O plus and apply the formula, you would get pH. In math, I think you all know that if you want to remove this negative sign from the formula, it would be what? pH equals what? Log 1 over concentration of H3O. Actually, we don't use this formula. We use this formula. But why did I write this? Just to drag your attention to one important relation, which is what type of relation between pH and H3O. It is inverse relation. Inverse means that in any solution, if H3O increase, pH would what? Decrease. In any solution, pH increase, H3O means that it is what? Less or decrease. Again, we don't use this formula, we use this one, but I have to write it in another way just to prove the inverse relation between both of them. Also, we have something called pOH. Also, it is a measurement for what? For basicity of solution. How much basic is the solution? And it is also given by its own formula, which is similar to one above, but instead of pH, it would be pOH equals minus log OH negative. And again, if we want to write it in another way, we could write it like this: pOH equals log 1 over OH negative, which means again that there is an inverse relation between pOH and OH negative. The solution which has higher concentration of OH negative would have a lower pOH value. The solution which has lower value of OH negative would have a higher value of pOH. Okay, now what are the values expecting? What is the range of values expected for pH or pOH? Let's talk about pH because it is much more used. pH is on a scale between the range of pH value starts from 0, ends by 14. This is the least value, this is the highest value that we are at least going to talk about in our book. Between them, the 7. Why do I choose 7 exactly to talk about? Why didn't I put any other number? Because this is the edge, this is the separating number between the acidic solution and the basic solution. How is that? Let's see. Now, any solution which has a pH value that is less than 7 till 0, it is considered what? Acidic solution. While any solution has a pH of greater than 7 to 14, it is considered what? Basic solution. Again, I'm talking about what? pH. Any solution which has a pH value less than 7 till 0, it is acidic solution. While if it has a pH of greater than 7 till 14, it is a basic solution. Why do I draw the relation as a triangle with its base to this side or to this side? This means that whenever you go down, this means that the value of pH would what? Would decrease if you go this side, this way. I'm talking about the acidic part. If you go below 7 to 0, the value would increase, decrease. When pH decrease, means that H3O becomes what? Higher in value. The H3O concentration would increase. And this means for any solution which has higher value of H3O plus concentration means that it is stronger. So this triangle here means that we are going from weak acid to what? Stronger acid. Again, because pH decrease, this means that H3O will increase. Any acidic solution with higher H3O plus concentration means it is stronger. So this triangle means that we are going from weak acid to stronger acid. On the other side, which is the basic side, if pH increase, let's talk about it. If pH increase means that in this solution, pH increase means that H3O would what? Decrease. But what did we say about OH negative concentration when H3O decrease? Again, look, you have to link these together. pH increase. This means that H3O goes down, decrease. What will happen to OH if H3O decrease? If H3O decrease, the OH minus would increase. And any solution has more OH value means more basic. It is stronger base. So the strength of the base is measured by how much pH it has over 7. Once the value increase, pH increase becomes more basic, stronger base. Once the pH for the acid, once the pH becomes down, once the pH becomes smaller, it means that it is greater or stronger acid. Now, if I want to put this in a relation, I can say like that. I don't know, just follow with me and check what I'm writing. Stronger acid would give what? Higher concentration of H3O plus, and this means lower concentration of OH minus. This leads to what? To higher H3O, معناته lower pH value. Let's check it together again. From where you want to start, I will go with you. Let's start from here. Lower pH value, compare one with 2 pH and one with 5 pH. Suppose that I have two acids, one of pH 2 and the other of pH 5. 2 here has lower, it is the lower pH value, so it has higher H3O plus concentration according to this relation. Higher H3O means it is stronger, so the stronger acid which has lower pH. This acid is stronger than this one. For base, suppose that you are comparing 9 with 10. Here, this one has higher pH value. Since it has higher pH value, so it has low concentration of H3O. Low concentration of H3O means high concentration of OH, which make it what? Stronger base. This is the relation. The last thing I am going to put as a relation is that pH for any solution, pH plus pOH all the time equals what? 14. all the time equals 40. So this is relation 1, this is the relation 2, this is the relation 3, and you would find that we can use these three relations together when we are going into calculations. Okay? Now, let's go into what? Calculations. Of strong acids. I will divide the calculation part into 4 parts. Calculations of strong acids, then calculations of strong bases, then calculations of weak acids, then calculations of weak bases. First of all, if we want to get the maximum benefit of this topic, we should first of all revise what is the list of the strong acids that we are talking about in this type of calculations. Again, I wrote it for you and mentioned these acids in the last video. Today I'm going to repeat them: HCl, HBr, HI, HClO4, HNO3, H2SO4. These are the acids that are considered, if you remember, 100% dissociation, and they are the strongest acid ever from the all acids we know. So this type of calculation is only using these acids, is only applicable for these acids. Any one of these, the question will not remind you with that if it is acid, strong acid or weak acid. No, you have to memorize this. Once you see any of these acids in a question, you know that it is a strong acid and you would apply the calculation that we are going to talk about now. First of all, if we use HX, for example, to represent the strong acid, whatever it is. Again, this is a general formula that I could use to represent a strong acid. HX would be what? HCl. It may be HBr. It may be HI. HClO4. This is the whole HClO4. This is the whole XNO3, and so on. If I use HX to represent the strong acid, the normal behavior of HX when it is dissolved in water is that, according to Bronsted-Lowry definition, this would give what? H plus, because the acid, according to Bronsted-Lowry, is a proton donor. This will give what? This will give you H3O plus, which is the part coming from H2O when it accepts the H plus, and the remaining part of HX would be what? X minus. For example, if I use HNO3 and dissolve it in water, it would give you what? H3O plus NO3 negative. If I use HClO4 plus H2O, it would give you H3O plus ClO4 minus, and so on. In this case, you remember that we are talking about 100% dissociation. If I want to put it as an ICE table, you remember the ICE table? Let me take one, or the general formula, HX plus H2O gives H3O plus X minus. Now, suppose, for example, I'm saying, for example, that I have 0.2 molar initial concentration of HX that I am going to dissolve in water. Now, this is before ionization. This is the initial amount that you are using, the initial concentration. After the 100% ionization, this amount would completely vanish, disappear, would completely dissociate. So this is what we mean by 100%. All the amount that you use it in the beginning would completely finish, disappear, and after the 100% ionization, the complete dissociation or ionization, by the way, dissociation is the same as ionization. After the 100% ionization or dissociation, this amount would completely disappear. Now, giving what? Giving, according to the ratio, this one has a ratio of 1:1 with H3O, which means the same amount here would appear for this one, which is 0.2. And also this is a ratio of 1:1 between the original acid and the X minus. For those who are asking what you mean by the ratio, here more ratio, this is 1, 1, 1, 1. So it means 1:1 ratio, means the same amount here would, when it is dissociating, it would give you the same amount of H3O, and also it would give the same amount of what? Of X minus, which is 0.2 molar. So you would get 0.2 molar of X minus and 0.2 molar of H3O plus. So can we generalize this idea? Yes, I can say in a solution of a strong acid, any strong acid, any one of these, once you know the concentration of the acid itself, it would be the same directly as the concentration of H3O plus and the same as X minus. Is it correct? The concentration of HX that we used in the beginning is the same as the concentration for both ions produced from the dissociation of the acid. So, in any strong acid, this is the most important part that I want you to listen carefully to me with it. If you know any one of these three, you would know the other two. Again, I am talking about strong acid. If in a question I gave you that X minus is 0.1, so H3O is 0.1, HX before dissociation is 0.1. If I give you that H3O is 1 times 10 to the power minus 3, so it means that X minus is 1 times 10 to the power minus 3, HX 1 times 10 to the power minus 3. If I give you that this one concentration was 1.5, so this one 1.5, this one 1.5. This is the most important part that don't forget, and we will use it intensively in calculations for a strong acid. For a strong acid. Now, let's go and have some applications on that. Question 1. You have 0.1 molar HCl solution. Calculate H3O plus Cl negative OH negative pH POH. Okay. Let's remember now. HCl is a strong acid. So HCl concentration would equal to H3O plus concentration equals to Cl negative concentration. Is it correct or not? It's supposed to be right according to what we have said before. So H3O would be what? Cl negative, 0.1 molar. I'm applying this formula. OH negative. Remember the formula Kw equals OH negative times H3O plus. This is all the time 1 times 10 to the power minus 14. We said it is all the time constant number. Now, I want OH. So, when multiplied by 0.1, which is H3O plus, I think now OH minus would be what? 1 times 10 to the power minus 14 over 0.1 equals 1 times 10 to the power minus 13 molar. This is one proof to what we have said. 0.1 is greater than 1 times 10 to the power minus 7, which is the reference for us. H3O increased compared to 1 times 10 to the power minus 7, which is the original case in which in water H3O is 1 times 10 to the power minus 7. Now, because I add HCl, H3O increased and become 0.1. What will happen when we said with that when H3O plus increased, what will happen is that OH will decrease compared to what? Compared to the original value of OH minus, which is 1 times 10 to the power minus 7. So compare these two with the original H3O plus and OH minus in pure water. You would find once this one increased compared to 1 times 10 to the power minus 7, this one decreased. But the total, when you multiply this by this, you would get all the time 1 times 10 to the power minus 14. What about pH? We said pH equals minus log concentration of H3O plus. This is pH. So it equals what? Minus log 0.1 what, and equals, you can go to calculator if you can't find it here, equals 1. POH, you can use two ways to find it. Either POH, let me just separate this part. Either you can find it as POH equals minus log OH negative, which equals minus log 1 times 10 to the power minus 13, and it would equal 13. Or you can say pH plus POH equals 14. So since pH is 1, so POH would give you what? 13. You can use either ways to calculate POH. This is one simple example for that. Another example, and I would go directly to, if you go back to the hand notes that I have written for you and sent it for you on Edmodo, you would find too many questions to practice these things, too many questions to practice. Just I'm giving you examples, solved examples, and you can use the idea here if you get it well, and solve the problems that I gave you before in the hand notes that I have submitted to you in Edmodo 2 weeks ago, I think. Now, let me go to question 2. HNO3 solution Look carefully to this question. Look carefully, very important question. HNO3 solution has a pH equals 3. 1. Or calculate one H3O plus 2 NO3 minus concentration POH concentration of OH minus. We, in this question, used H3O to find pH. Now the question is here, giving me the pH, and I'm required to find H3O. Do you find the difference? Here, we find H3O and use it to find pH. The question here gives me the pH and asked for H3O. So I can't use the same formula here. This formula is used to calculate pH whenever you have H3O plus, but here you don't have it. You are required to find it here. So I have to play with this formula, and it would be like this. Look carefully. In this case, if I have the pH value and I want to find H3O, this would become like this. H3O plus equals 10 to the power minus pH. By the way, it is a mathematical way that I have used to change this formula to this one. What is the difference? The difference here is that you calculate pH when you find or you have H3O. Here, I need to calculate H3O from pH. I have to use this formula directly. Now, this means that H3O plus equals 10 to the power minus, what is pH? 3. This is the concentration of H3O. Now it is already solved. Again, since this one is strong acid, so H3O equals the negative part, as we said before. So this one would be what? Also 10 to the power minus 3 molar. POH, since pH plus POH equals 14, pH is 3 plus POH equals 14, so POH equals 11. So what about OH? OH, I can find it by two ways. First of all, I can say that OH minus equals KW over H3O plus which comes from this formula, the same one. I want OH, I divide KW over H3O plus, or I can use the same as we use it here, which is what? Concentration of OH minus equals 10 to the power minus POH. Here, this one equals what? 1 times 10 to the power minus 14 over what? Over 10 to the power minus 3, which equals what in this case? Equals 1 times 10 to the power minus 11. Here, also, if I use this way, 10 to the power minus, what is POH? 11. It would be the same in both cases. It would be the same in both cases. This is the maximum ideas that I can give you here for strong acids. I will go to strong bases and end my video with it. Calculations of strong bases. look carefully here. There is one difference between the calculations of strong acid with strong bases, or from strong base. Why is that? Because we have two types of strong bases. One of them is monohydroxide, which means it contains one hydroxyl group in it, like LiOH, NaOH, KOH. They all have one OH group in their composition. The second type of strong bases also has OH, but instead of one group, it has two groups of it, like CaOH by 2, BaOH by 2, SrOH by 2. These are the only strong bases, that we are going to talk about. But the difference here is that they all contain here two OH. How would one OH group in the composition of a base make the calculations differ than the one which contains two? Let me see. Now, let me tell you one important thing. If I represent this or these bases as DOH, in which D represents either Li, NaK, and for these I would use DOH by 2. What will happen here is that DOH, when dissociates in water, when it is in water, it would give you what? DOH. It would give D plus OH minus. While for this one, it would give what? D plus 2, Ca plus 2, Ba plus 2, Sr plus 2, plus 2OH negative. This is the important thing that differs this one from this one. What would be the difference? In this case, as you can see, the ratio here is 1 to 1. The ratio between this and this is also 1 to 1. So I can say that in this case, DOH concentration equals OH negative equals D plus. So once you know any of these three, you would know the other two. But what is the relation in this case? In this case, here is 1 to 1, which means that DOH by 2 equals D plus 2 concentration. This one would be the same as this one, but the problem is with the OH. While OH would become over 2, because the ratio with this one is 1 to 2, or with this one is 1 to 2. What does that mean? All the time, OH is twice the amount or twice the concentration of D plus 2. So if you divide OH by 2, you would get the same concentration of D plus 2. This is what we mean here. Again, according to the ratio 1 to 2 here, OH is twice the concentration of D plus 2. OH negative, the concentration of OH negative is twice the concentration of D plus 2, which means if you divide the concentration of OH by 2, you would get the same concentration of D plus 2. This is what we did here. And also the ratio between this one, which is the original base, with the OH is 1 to 2, which means again, in the solution of this base, which contains two OH groups, the concentration of OH would be twice the concentration of the original what? Base. So if you divide OH by 2, you would get the same ratio or the same concentration of the OH plus 2, which you can get it from here. If you look at this two sides, if you divide OH by 2, you would get the original concentration of the OH by 2. This is the difference between both cases. And this what will affect the This what will affect the calculations. Let's have questions and check for these relations together. I would go directly to give you the question with the simplest way. Suppose that I have 0.1 molar KOH. Calculate OH negative K plus pH POH. Since it is a monohydroxyl base, which means that it has only one OH, so the ratio between the KOH, the original one, and both of these is the same. So this one would be what? 0.1. This one would be also 0.1. pH equals what? This is the idea here. If you want to find pH, the formula of pH is what? pH equals minus log H3O, but I don't have H3O. So it is biologic that I need to find the concentration of H3O plus. Where from I can get it? I can go here and make a side calculation. H3O plus equals Kw over OH minus, which is the formula that all the time combines the H3O with OH, which is all the time Kw 1 times 10 to the power minus 14, which is a constant all the time. OH is what? 0.1. So H3O is what? 1 times 10 to the power minus 13. So now I can use it here, which equals minus log 1 times 10 to the power minus 13, which equals 13. This should be done before this one, because you can't find pH without H3O, and I don't have H3O. I have to find it from the relation between H3O and OH in any solution. POH, you can go either say POH equals 14 minus pH. Don't say that it is a new formula. It's the same. When we say pH plus POH equals 14, so any one of these would be 14 minus the other one, which means 14 minus pH 13, POH equals 1. Or you can say POH equals minus log concentration of OH minus equals minus log 0.1, and also it would give you 1. Again, in the handout I submit for you last week or the week before, you would find too many calculations about that. You can practice yourself for it. Let's take now one example of these to see the difference. Dihydroxyl bases. Suppose that I have 0.5 molar of CaOH by 2. I can put for myself, it is not supposed to be done. If you want, just make the dissociation equation for it. You would get Ca plus 2, which I was writing as D plus 2 before, plus 2 OH minus. Okay, it's for me. It is not supposed to be written, just for me. Now, if I want to find OH minus, if I want to find H3O plus, if I want to find pH, if I want to find POH, and so on. If I want to find, for example, Ca plus 2. Now, remember the formula that combine these all together because you are going to use it now. Again, I will put it here. Ca OH by 2 equals Ca plus 2 equals OH minus over 2. This is the formula. So, OH, I need this one. So I have to multiply 2, cross multiplication. Suppose that this part is not found. Suppose that this part is not found. You have to multiply 2 by the concentration of CaOH by 2 to find OH. So it would be what? 2 times concentration of CaOH by 2 equals 2 times 0.5 equals 1 molar. H3O plus equals H3O plus equals Kw over OH minus, which equals 1 times 10 to the power minus 14 over 1 equals 1 times 10 to the power minus 14 molar. This is the concentration of H3O. pH equals minus log H3O plus equals minus log 1 times 10 to the power minus 14 equals what? 14. POH equals 14 minus pH equals 14 minus pH is 14. pH is 14 also, so POH equals 0. And don't forget, when we give you the scale of pH, it was starting from 0 to 14. So we have 0 pH or POH. Concentration of Ca plus 2, this one. You can either say it equals to this one or it equals to OH over 2. So you can use any of these, either relate this with this one or relate it with this one. If you say Ca plus 2 equals OH minus over 2, it would be what? What is the OH minus? 1 over 2 equals 0.5 molar. Or you can say concentration of Ca plus 2 equals this one equals this one, Ca OH by 2. What is the Ca OH by 2? It is 0.5, so it would give you the same answer. This is the difference here. Last question. A solution of BaOH by 2 has a POH or pH. Let me start with pH. Equals 9. Calculate. Concentration of OH minus. Look carefully here. I have a pH. pH can give me concentration of H3O. Then the second step, I will convert H3O into pH. So to solve this one, out of this one, you have to pass by several steps. The first step is, now I would find H3O plus from this relation by using, you remember when I say that if you have a pH, you should use H3O equals 10 to the power minus pH, which equals 10 to the power minus 9 molar. Second step, from the Kw, I would find OH minus equals Kw over H3O plus, which equals 1 times 10 to the power minus 14 over 1 times 10 to the power minus 9 equals 1 times 10 to the power minus 5 molar. This is the OH. Now, if I want concentration of BaOH by 2. Now, don't forget the relation here. BaOH by 2 concentration equals Ba plus 2 equals OH minus over 2. So to find this, you only need to do that. It equals what? OH minus over 2, which equals 1 times 10 to the power minus 5 over 2 equals 0.5 times 10 to the power minus 5 molar, and this is the end. Okay? Thank you very much. You can go back to what has been given to you. As I told you, the hand notes that was submitted to you in the last 2 weeks, I think. You could find too many questions to solve and practice yourself on that. I hope it was somehow an explanation for the calculations for strong acids and bases. In the next, inshallah, video, we are going to talk about the weak acids and bases together. Thank you very much.